Welcome to our deep dive into the world of 20th century physics. We'll be exploring excerpts from 20th century science physics to uncover the pivotal discoveries and groundbreaking theories that shaped this era.
It's a fascinating journey that takes us from the subatomic realm to the vast expanse of the cosmos.
And it all starts in the early 1900s.
A period where the seemingly solid foundation of classical physics began to crumble.
It's like cracks appearing in a seemingly perfect structure, hinting at a deeper, more complex reality beneath the surface.
And one of the first cracks was the discovery of the electron in 1897.
J.J. Thomson, right, with his cathode ray experiment.
Exactly. His experiments revealed these tiny, negatively charged particles much smaller than atoms.
Shattering the prevailing view of atoms as indivisible, fundamental units of matter.
Precisely. It was a pivotal moment marking the beginning of our journey into the intricate world within the atom.
And then there was black body radiation, another puzzle that classical physics couldn't quite solve.
Right. Classical physics predicted that the energy emitted by a heated object should increase infinitely as the wavelength decreased, but experimental observations showed a peak in energy emission at a specific wavelength.
So how did physicists reconcile this discrepancy?
Max Planck proposed a revolutionary solution in 1900. He suggested that energy was not emitted continuously, but in discrete packets called quanta.
Quanta, like little bundles of energy.
Yes, and the energy of each quantum was proportional to the frequency of the radiation, captured in his famous equation E equals h.
Where h is Planck's constant, of course.
Precisely, Planck's quantum hypothesis, though initially met with skepticism, laid the foundation for the development of quantum mechanics.
It was a paradigm shift, a radical departure from classical physics.
It fundamentally changed our understanding of energy and its interaction with matter.
And then we have the discovery of radioactivity, which further shook things up.
Henri Becquerel stumbled upon it in 1896. He found that uranium salts emitted invisible rays that could penetrate opaque materials.
Quite by accident, as I recall.
Indeed. It was a serendipitous discovery that revealed the inherent instability of certain elements,
And hinted at powerful forces at play within the atom.
leading to further investigations by Marie and Pierre Curie, who isolated new radioactive elements like polonium and radium.
It's amazing how these early discoveries set the stage for a revolution in physics.
They challenged long-held beliefs and paved the way for new theories that would reshape our understanding of the universe.
And speaking of revolutions, no discussion of 20th century physics is complete without Albert Einstein.
Yes, Einstein. His theories of relativity truly transformed our understanding of space-time gravity and the nature of reality itself.
1905 was his miracle year, wasn't it?
Yeah.
Publishing 4 groundbreaking papers.
It was his annus mirabilis. He addressed the photoelectric effect, Brownian motion, special relativity, and the equivalence of mass and energy.
Let's focus on special relativity for a moment. It challenged the idea of absolute space and time.
In classical physics, space and time were considered absolute and immutable, but Einstein proposed that they were relative.
Relative to the observer's motion.
Exactly. He based special relativity on 2 postulates. The laws of physics are the same for all observers in uniform motion, and the speed of light in a vacuum is constant for all inertial observers.
2 simple postulates with mind-boggling consequences.
Indeed, time dilation, length contraction, the idea that mass and energy are interchangeable, these were radical concepts,
But they were later confirmed by numerous experiments.
solidifying special relativity as a cornerstone of modern physics. And then there's general relativity, which provided a new way of understanding gravity.
No longer a force acting at a distance, but a consequence of the curvature of space-time.
A truly revolutionary concept.
It's fascinating how Einstein's theories revolutionized our understanding of the universe on the largest scales.
While at the same time, another revolution was brewing in the realm of the very small, the development of quantum mechanics,
A theory that describes the behavior of matter and energy at the atomic and subatomic level.
where things get really strange.
One of the key concepts is wave-particle duality.
The idea that particles like electrons can exhibit both wave-like and particle-like behavior.
The double-slit experiment is a classic example. Electrons passing through 2 slits create an interference pattern, just like waves.
It's a mind-bending concept challenging our classical intuitions about the nature of matter.
Another key concept is the quantization of energy.
Building on Planck's work, Niels Bohr proposed that electrons in atoms could only occupy specific energy levels.
His model successfully explained the spectrum of light emitted by hydrogen, but it was still incomplete.
Further developments came with wave mechanics by Erwin Schrödinger and matrix mechanics by Werner Heisenberg.
2 different approaches that ultimately proved to be equivalent.
providing a more comprehensive description of quantum phenomena,
But perhaps the most unsettling concept in quantum mechanics is Heisenberg's uncertainty principle.
which states that there is a fundamental limit to how precisely we can know certain pairs of physical properties of a particle.
Like its position and momentum.
This principle challenged the classical notion of a deterministic universe, where the future could be predicted with perfect accuracy if we knew the initial conditions.
Quantum mechanics introduced an element of uncertainty and randomness into our description of the universe.
Suggesting that at the quantum level, events are not predetermined, but governed by probabilities,
It's a profound shift in our understanding of reality.
with far-reaching implications for our interpretation of the natural world.
So these early developments in quantum mechanics laid the foundation for a field that continues to evolve and challenge our understanding of the universe.
A field that has had a profound impact on our lives through countless technological innovations.
From transistors and lasers to nuclear power and medical imaging.
It's a testament to the power of scientific inquiry and the transformative impact that fundamental discoveries can have.
As we continue our deep dive, we'll explore how these groundbreaking discoveries in the early 20th century set the stage for even more astonishing revelations in the decades to come.
From the exploration of the nucleus to the mysteries of cosmic rays and the development of the standard model of particle physics,
It's a journey that will take us to the very frontiers of human knowledge.
revealing the interconnectedness of the universe and the power of the human mind to unravel its secrets. The first half of the 20th century really was a golden age for physics, with groundbreaking discoveries reshaping our understanding of the universe at both its largest and smallest scales.
It's just incredible how these seemingly disparate realms, the cosmos and the subatomic world, became increasingly intertwined as physicists delved deeper into the mysteries of nature.
And this interconnectedness becomes even more apparent as we move into the mid-20th century, where advancements in nuclear physics and cosmic ray research would further expand our understanding of matter and the forces at play within the universe.
Let's start with nuclear physics, a field that emerged from the discoveries of radioactivity and the structure of the atom. What key developments in this era would you say were most significant?
One of the most crucial discoveries was the neutron in 1932 by James Chadwick.
Yes.
The neutron.
This electrically neutral particle, residing within the atom's nucleus alongside the positively charged proton, helped explain discrepancies in atomic masses and opened up new avenues for exploring the nucleus.
The neutron's discovery seems to have been a turning point, providing a more complete picture of the atom and its constituents.
Absolutely. It also provided physicists with a new tool for probing the nucleus. Unlike charged particles, neutrons could penetrate the atom's core without being repelled by the positively charged protons. This led to Enrico Fermi's pioneering work on neutron-induced radioactivity.
Where he bombarded various elements with neutrons right.
Precisely, creating a plethora of new radioactive isotopes.
Fermi's work had profound implications, didn't it? Both for our understanding of nuclear processes and for the development of technologies like nuclear reactors and weapons.
Precisely. His research is testament to meticulous experimentation and keen observation laid the groundwork for both the peaceful and the destructive applications of nuclear energy. Speaking of exploring the nucleus, how did the development of particle accelerators revolutionize experimental physics?
Particle accelerators, born from the ingenuity of physicists like Ernest Lawrence and John Cockcroft, enabled us to create controlled beams of high-energy particles, smashing them into each other to study the subatomic debris.
These accelerators became indispensable tools for probing the fundamental constituents of matter and the forces that govern their interactions.
These machines, essentially giant microscopes, allowed us to peer into the heart of matter, revealing the building blocks of our universe. The first cyclotron, built by Lawrence in the 1930s, was a relatively small device, but it paved the way for the development of increasingly powerful accelerators.
Culminating in today's behemoths, like the Large Hadron Collider.
Exactly. And the discoveries made using these accelerators, from the confirmation of the standard model of particle physics to the discovery of the Higgs boson, have been nothing short of revolutionary.
It's a testament to human ingenuity and our relentless pursuit of understanding the universe at its most fundamental level. Now, while particle accelerators were probing the subatomic world, cosmic ray research was providing another window into the realm of high-energy particles.
Cosmic rays, these high-energy particles bombarding Earth from outer space, provided a natural laboratory for studying subatomic particles.
A natural source of high-energy particles.
Precisely, scientists like Victor Hess and Carl Anderson made groundbreaking discoveries using cloud chambers to track these cosmic particles. Anderson's discovery of the positron, the antimatter counterpart of the electron, was particularly significant.
Antimatter, a concept straight out of science fiction, was now a confirmed reality. What implications did this discovery have for our understanding of the universe?
It was the first experimental confirmation of Paul Dirac's theoretical prediction of antimatter. The existence of antimatter, where particles have the same mass but opposite charge, opened up a whole new realm of possibilities in particle physics.
And it raised profound questions about the nature of the universe, didn't it?
Absolutely. The possibility of antimatter galaxies, or even anti-universes, questions that still intrigue cosmologists and particle physicists today.
And these discoveries, both from particle accelerators and cosmic ray research, were feeding into the development of the standard model of particle physics.
The Standard Model, a triumph of 20th century physics, classifies the fundamental particles into two categories: fermions, which make up matter, and bosons, which mediate forces.
It's remarkable how physicists were able to piece together this intricate puzzle of the subatomic world, identifying the fundamental constituents of matter and the forces that bind them together.
It has successfully explained a wide range of experimental results and predicted the existence of new particles, solidifying its place as one of the most successful theories in physics.
However, the standard model, while remarkably successful, is not a complete theory.
It does not include gravity, one of the four fundamental forces, and it leaves some fundamental questions unanswered. Questions about the nature of dark matter and dark energy, the hierarchy of particle masses, and the unification of all fundamental forces, including gravity, into a single theoretical framework. These questions continue to drive research in particle physics and cosmology today.
Speaking of unifying forces, let's talk about string theory, a candidate for a unified theory of everything that emerged in the latter part of the 20th century.
String theory proposes that the fundamental constituents of the universe are not point-like particles, but rather tiny vibrating strings.
Strings.
Yes. Different vibrational modes of these strings would correspond to different particles and forces, offering an elegant explanation for the diversity of the subatomic world.
It's a fascinating and ambitious theory, pushing the boundaries of our imagination and challenging us to rethink the very nature of reality.
Though mathematically complex and yet to be experimentally verified, it has captivated the imagination of many physicists and holds the potential to revolutionize our understanding of the universe.
However, it's important to acknowledge that string theory is still under development. There are many challenges to overcome, both theoretical and experimental, before it can be considered a fully fledged theory of everything.
Absolutely. But that's the beauty of science. It's a continuous process of exploration, questioning, and refinement. And as we move into the latter decades of the 20th century, we see this process accelerating, driven by technological advancements, like electronic computers.
Computers initially developed for mathematical calculations have revolutionized not only our daily lives, but also the way physics research is conducted.
Indeed, they became indispensable tools for analyzing data, simulating complex systems, and developing theoretical models, enabling physicists to tackle problems that were previously intractable.
From astrophysical simulations of galaxy formation to quantum mechanical calculations of atomic and molecular properties, computers became essential partners in the quest to understand the universe.
And as computing power continues to grow, so too does our ability to explore the frontiers of physics.
Speaking of unforeseen advancements, let's talk about the discovery that shook the foundations of our understanding of the universe, the accelerating expansion of the universe.
In the late 1990s, two independent teams of astronomers studying distant supernovae made a startling observation. The expansion of the universe was not slowing down as expected, but rather accelerating.
This discovery, which earned the 2011 Nobel Prize in Physics, challenged our understanding of gravity and led to the introduction of a mysterious force dubbed dark energy.
Dark energy, a repulsive force that counteracts gravity, is thought to be responsible for the observed acceleration. But its nature remains elusive.
A mystery that continues to baffle physicists.
We don't yet understand what dark energy is, how it works, or why it exists. This mystery of dark energy, alongside the equally enigmatic dark matter, represents one of the greatest challenges in modern cosmology.
It's a humbling reminder that despite our remarkable progress in understanding the universe, there's still so much we don't know. And that's what makes physics so exciting. There's always a new frontier to explore, a new mystery to unravel, and a new challenge to overcome.
As we conclude our exploration of the mid to late 20th century, we see a recurring theme of interconnectedness. Discoveries in one area of physics often have profound implications for other areas, leading to a deeper and more unified understanding of the universe. And this trend continues into the 21st century as physicists build on the legacy of the 20th century, pushing the boundaries of knowledge and seeking to answer the fundamental questions that remain.
As we reach the end of our deep dive into 20th century physics, it's clear that this era laid the foundation for our modern understanding of the universe.
It was a century of profound transformation, marked by a relentless pursuit of knowledge and a willingness to challenge long-held assumptions.
And while we've explored the contributions of giants like Einstein, Bohr, and Heisenberg, it's important to remember that scientific progress is often a collaborative effort.
Countless individuals, some renowned and others less so, worked tirelessly to expand our understanding of the natural world.
One such individual is Lise Meitner, whose crucial role in the discovery of nuclear fission was often overshadowed.
Her story serves as a reminder of the importance of recognizing the contributions of all scientists regardless of their background or gender.
It also highlights the power of collaboration and the importance of diverse perspectives in scientific inquiry.
Diversity in science is not just a matter of fairness. It's essential for the advancement of knowledge itself.
Different perspectives and experiences can lead to new insights and breakthroughs, enriching our understanding of the universe and its complexities.
Now, as we reflect on the legacy of 20th century physics, it's important to acknowledge the intersection of science and society.
Physics is not just an abstract pursuit. It has real-world implications influencing technology policy and even our understanding of our place in the universe.
We saw this most starkly with the development of nuclear weapons, a testament to the power of physics, but also a sobering reminder of its potential for destruction.
The atomic bomb forced humanity to confront the ethical and societal consequences of scientific advancements.
It raised profound questions about responsibility control and the dual nature of scientific knowledge.
These questions are still relevant today as we grapple with emerging technologies like artificial intelligence and genetic engineering.
It's crucial for scientists to engage with the public, to communicate their findings clearly, and to participate in discussions about the implications of their work.
And for the public to be informed and engaged, to contribute to shaping the future direction of science and technology.
Science literacy is essential in today's world, empowering individuals to make informed decisions and to participate meaningfully in the dialogue surrounding scientific advancements.
So as we conclude our exploration of this remarkable era in physics, what key takeaways would you say stand out?
I think one of the most striking takeaways is the interconnectedness of different areas of physics.
From cosmology to particle physics, seemingly disparate fields found themselves intertwined, each informing and enriching the other.
This interconnectedness extends beyond physics itself, into other scientific disciplines like chemistry, biology, astronomy, and engineering.
Physics provides the foundational principles that underpin our understanding of the natural world.
It's the science of matter-energy and their interactions, and as such, it plays a role in virtually every aspect of our universe.
Another key takeaway is the sheer pace of discovery during the 20th century.
From the electron to the expanding universe, physicists were constantly pushing the boundaries of knowledge, overturning long-held beliefs, and revealing the universe's hidden workings.
It was a century of revolutionary breakthroughs, driven by brilliant minds and an insatiable thirst for knowledge.
So as we bid farewell to the 20th century and its remarkable legacy in physics, what message would you leave our listeners with?
I would echo your earlier sentiment. The pursuit of knowledge is a never-ending journey.
The 20th century laid a foundation of groundbreaking discoveries, but there are countless mysteries still waiting to be unraveled.
Stay curious, stay engaged, and never stop exploring the wonders of the universe.
And who knows? Maybe one of our listeners will be the next Einstein, Bohr, or Meitner.
Pushing the boundaries of physics and reshaping our understanding of reality.
Here's to the future of physics and the endless possibilities it holds.
To the future of physics, and to our listeners. Thank you for joining us on this deep dive into the fascinating world of 20th century physics.